Hello, everyone. I'm going to be talking to you about the theoretical motivation behind something that Parker Solar Probe observed a few years back. So I just want to start off by three main vocab words: Parker Solar Probe, solar winds, and interchange reconnection. So hopefully we'll give you an idea of what that means, and then I can get into my actual work. So Parker Solar Probe, in all its glory, Parker Solar Probe was a mission designed to touch the sun, fly by the solar corona, and it did exactly that not too long ago. You can kind of see it in this photo here. And so I'm taking some of that data on what's known as the fast solar wind. So the solar corona, the surface or the waves around the sun generate two types of waves, fast and slow solar waves or wind. And my project mainly looked at the fast ones, which are on the poles of the sun. So the reason we're looking at these, or we have observations of these, and a motivation behind what generates the fast solar wind is what's known as interchange reconnection. That's kind of the theoretical understanding behind it. And to understand that, we need to first look at what's called magnetic reconnection. So magnetic reconnection is, as it's shown here, breaking and rearranging of oppositely directed fields. So you have a lot of snapping fields that generate a lot of kinetic and thermal energy, and this takes place in various systems beyond just the sun, also in black holes, also in the aurora borealis, if people remember from a few months ago. So it's a very it's a very common system that happens in a lot of different regions. I'm specifically looking at what's called interchange reconnection. So instead of having two straight field lines, you have these loops or closed field lines. You can imagine this being the surface of the sun, and you have these loops forming, and then you have straight field lines, and then interchange reconnection is the interaction between those two types of field lines, creating these switchbacks which propagate out from the surface of the sun, or from the surface of the corona. So we believe that this is what's driving the fast solar wind that we observe, because characteristics of the solar wind are what's shown here: bursty flows, ambient solar winds, reduced magnetic pressure, and bursts of energetic ions. And then if you're following what I'm saying, that's exactly what interchange reconnection also gives us. And then we see these trends in the actual observed Parker data, which is shown on the right. Didn't realize there was going to be no Q&A, so if you have questions, please come by my poster. And so the way we model this is by using kinetic particle and cell simulations. So essentially what we're doing here is we're packing a lot of high energy particles into this grid-like system and iterating it through by enforcing Maxwell's laws on them. A lot of math, a lot of physics that creates a lot of really cool outputs. And so in order to do this, we can't really just put like a random solar surface in our simulation. So what we do is we flip it symmetrically to make a circle of closed field lines and then straight open field lines, and then create this bundle and a straight field line. So this is what some of our outputs look like. So this was the initial trend or the initial system that we tried, but it wasn't really accurate to what's actually going on because there's many open and closed field lines. So we essentially doubled it up. And so we put two closed bundles in, two open field lines between them, and then looked at what happens after that. Hopefully it should be, okay, great. So here you can see a movie of the actual system. Now, again, remember, right along the center is what the solar surface would look like. So obviously you don't have actual circles on the surface of the sun, but we hope to what would be going on. And if it plays, it's kind of a slow start like most things are, but then once it starts going, you can see that these bundles are moving through the open field lines. And then if you remember the graphic from a few slides ago, you have these straight, where's my, oh no, you have these straight things shooting off. So that's exactly, so that's exactly what we wanted to observe. In our initial condition, we have the two bundles just stagnant, and then we have a first reconnection. We enforce periodic boundaries, which essentially means anything that exits out the right also comes back through the left. And so we have this repeated reconnection going. So along the surface of the sun, we have things moving to the right, coming back, and just reconnecting with each other again and again, which is pretty exciting. And then for the next few slides, I want you to remember these two numbers here, 50 and 100, which is precisely approximately where each of these reconnection events happened in my simulation, because we also see more results that give us more indication of what the driving force of the fast solar wind is. So if you remember from before, asymmetric bursts were one of the features of the solar wind that interchange reconnection also justifies. And then if we remember 50 and 100 from before, we see spikes at those values, which is quite quite compelling. And we also see the asymmetry that I mentioned. So we have a wider spike here and a more narrow, higher peak for 100, and same thing going on in time, which is pretty exciting because those are actual Parker results that we observed from the run a few years ago. Another thing that we see is what's called radial flux of exhaust. So one of the signatures that we found from the Parker data were these repeated peaks along the spatial direction. So we took this snapshot of at time step 50, cut a horizontal line in X, and then plotted what the flux looked like for several times, which are listed here. And then again, looking at that 50 and 100 time step, we can see two of these peaks, which are moving in space, which is pretty compelling when you compare it to this one plot that one of my mentors, Professor Jamie Drake, made in a paper, I want to say 2021, where this was a cartoon of what we'd expect to see in the flux from our model. So you have each of your flux loops and the open field lines, and then as they reconnect, we expect to see these peaks. And then that's exactly what I saw from my data, which is pretty exciting. So we have pretty compelling evidence that interchange reconnection is in fact what's driving these fast solar wind. And it's pretty exciting. So while I leave this up, I want to talk about what we were planning to do next. So one of the things that we noticed, essentially we're just trying to make the model as accurate as possible. So we have our straight field lines that are kinking a lot. We want to try to curve that so we can have even more reconnection, which is always really exciting. And we want to get some more of these peaks if possible. But yeah, very fruitful summer. Huge thanks to everyone in this room, those who I know and those who I don't. And yeah, if you have questions, please come find me during my poster.